Okay, so let us start with the afternoon session. So we have Loka, and he will be telling us about influence functional.
Okay, so what I wanted to talk to you for the next hour is a set of things that I and various collaborators of mine have been thinking about and worrying about for last few years. Well, slightly more than a year. So what I'm going to talk about are influence functionals and their structure and renormalization. So I suppose most people here would probably not know what influence functionals are, so I will start with what they are. But before that, let me just give some of the references, like which I'll be covering. So one is a paper which we wrote on OTOCs, out of time ordered correlators, and so on and so forth, with Felix and Prithvi Narayan, who was a postdoc at ICTS then, and Mukund, and another paper which is so with Avinash, who was a student at ISC and who is now at Davis, and Chandan and Arnab. So Chandan is a student here, and Arnab is a postdoc at ICTP. So I think various time zones are all covered among. So anyway, so this is with Felix, with we. And Amin, who was a postdoc here and is now at ISC, and Mukund. Okay, so and then there are various other works which all has to be written up with one of my students here, Soumyadeep, and a summer student from IIT Guwahati, Chandramouli. And Chandan, I guess, and Akhil, Disha, and many people. So yeah, so all from ICTS. Okay, so what I'm going to talk about is basically a set of works that are yet to be finished, and so half of it will be things that are already there, and the other half will be things that are yet to be like put on archive. Okay, so let me just start by trying to explain this title, what influence functionals are. So this name influence functional is originally due to Feynman and Vernon, like who in 60s came up with this idea to describe what I guess what they did not call it, but what is now many people would call as an open quantum systems. So these are quantum systems which are in contact with environments. So in the sense that so they don't evolve unitarily. So basically, you can think of there being an environment, some cartoon like this, and you have a system where the environment plus the system they evolve unitarily. But if you just think about the system, so which is as good as just a part of a system, part of a quantum system, it doesn't necessarily evolve unitarily. And the influence functional was a way that Feynman and Vernon argued that you should describe the non-unitarity in the evolution of the system. So so how do you describe the non-unitarity in the evolution of a part of a system? And what they try to do is to characterize it. So that is the couplings and the interactions which are responsible for the non-unitarity. Via like some terms in the action, if you want, some effective action, which will become more clear. And they call it influence functional. I guess their intuition was that this kind of characterizes the influence of the environment on the evolution of the system, and hence the name. Okay, so the way they did it, so yeah. So you have, you can think of, if you think of it as Hamiltonian, so you have some interaction, and what you want to know is and the state is also something in the Hilbert space, combined Hilbert space of the system plus the environment. And what you want to know is the evolution of rho system, the reduced density matrix of the system, okay, and which is basically trace over the environment of the rho system plus environment, okay, and the question is that, you know, like, how does it evolve, okay, so that is the and how do you describe this evolution in path integral language? So you can describe such an evolution in many different pictures. And Feynman and Vernon used the path integral language, which will be more conducive. And what I will be talking about is you know, like a particular subset of such things which applies to quantum field theories. Okay, so I'll be talking about influence functions in quantum field theories, in particular in relativistic quantum field theories. But the general idea is a very common idea. So what they were interested in particular, is to come with a path, come up with a path integral. So you want a path integral which captures you know, like time ordered correlators of the system variables. So you can say some operators in the system, and let's say, you know, like evaluated in some rows, in the sense that, you know, like you start with some initial density matrix. So you're given, let's say, the system density matrix at time t equal to 0. Okay, then their question was, and let's say you want to ask a question of what the correlators are at various times, say future times, time ordered correlators, and the point is that, you know, like, and then how do you do that? Okay, so it's not even clear that, you know, like this question necessarily has an answer, because, you know, like obviously the system is not the complete information. It often depends on what the environment is doing. So, but if I don't give you that information, if I just give you what the system is doing, it's yeah, generally it is clear actually that, you know, like you cannot just answer this question with just the information about the system state. So, you know, like what this needs is some assumptions about the environment, okay, under some reasonable assumptions of environment. So, for example, one common assumption which is often useful is to say that environment is like a bath, it's a thermal bath, okay, it's the bath of harmonic oscillators, let's say, which are, you know, like in a thermal state, and assume that, you know, that is the initial state, and the evolution is just that there's harmonic oscillators. So you know, like this kind of a question necessarily needs some assumptions about the environment, but under some assumptions about the environment, what they argued is that, you know, you can write down a path integral which actually calculates its correlators. Okay, so what they did is, so they did not characterize it that way, but what they did can now be thought of as basically thinking about a Schwinger-Keldysh effective action. Okay, so I will, for the system. So that's what they derived. Okay, so the point is that, you know, like so let me just remind you. So Mukund already talked about Schwinger-Keldysh formalism in his first talk, but let me just remind you, how does this work? So for any quantum field theory, okay, so you can write down a generating function of correlators, generating functional of correlators, which are basically of this kind, where you have some anti-time ordered. So this means anti-time ordered. Okay, correlators, and then some time ordered correlators. Okay, evaluated on some time t equal to 0. So and this generating functional is what is called as a you know, what I'll denote it by ZSK. So I will denote the so this is usually a functional of two sources. So like in any other quantum field theory, the generating functional of correlators can be written as a function of sources, where these right forces give you the time ordered correlators, whereas the left sources, if you differentiate, they give you the anti-time ordered correlators. For example, like if you can differentiate this functional some number of times with respect to the right source, some number of times with respect to the left source, and then like what you get is a time ordered correlators of the operators coupled to the right source, and the anti-time ordered correlators of the operators coupled to the left source. Okay, and that is what a Schwinger-Keldysh function is. And if you have an action and so on and so forth, you can write it as basically. So let's say you take a copy. Let's say phi is my field, and then you have an action which is like S of phi r minus S of phi l. Okay, so this generates the time ordered correlators. This generates anti-time ordered correlators with the initial condition that phi r phi l at t equal to I or t equal to 0 are given by the initial density matrix. This rho t equal to 0, and at t equal to infinity, you set phi r equal to phi s. So that and you sum over all possible phi r and phi l at t equal to infinity, which is basically like another way to say it is that you do an integral over a path integral over a time contour. So this is a time contour, okay, where like you go forward in time. So you insert a density matrix at t equal to 0. You go forward in time, and here basically identify and sum over various things. Okay, so the point is that like this computes in any unitary quantum field theory. This also computes the time ordered and anti-time ordered correlators. You can ask like for quantum field theorists, like you can ask how does it look like. Let's say if you have a weakly coupled theory, how do the Feynman rules of such a theory looks like. So you can just start with, let's say, a phi 4 theory. So you can take S of phi to be minus integral, let's say d4x del phi square plus m square phi square plus lambda phi to the power 4. Okay, so and then like you can ask what does this give you? Okay, so this is just the ordinary phi 4 theory. So what it gives you is a usual, so time ordered correlators. We already know what the Feynman rules are. So the Feynman rules are basically, you have a propagator like this, and which is like minus I over p square plus m square minus I epsilon, and then you have a quartic vertex, which is given by minus I lambda. Okay, but the point is that like so this is really the right guy. But but what happens if you're calculating a Schwinger-Keldysh correlators or Schwinger-Keldysh functional is that to this you also add. So I will denote by this the left correlator, the anti-time ordered fields. So like which is given by the anti-Feynman and then like you have an anti-Feynman vertex which is given by I lambda. Okay. So basically like what you have is the propagator of this guy is a complex conjugate of the time ordered fields that you're familiar with, and the vertex is also complex conjugate, and then you can just go on calculating, and but like so you can see that till now there is no linkage between the right and the left. So it seems like I've just doubled the two fields, except that like I have some funny propagator and a funny vertex, but this is not entirely true. Because of the particular boundary condition, so these boundary conditions, so this actually, so I'm doing it with the vacuum. So I'm taking rho t equal to 0 to be the vacuum of the this thing. So that's what gives you this propagator. But the point is that like so this is taken care of, but this boundary condition means that like the phi r and phi l are actually coupled, and the coupling actually arises by what I call as cut propagators. Okay, which are basically of this form, which couple the right fields, the time ordered fields, with the anti-time ordered fields, and this is basically given by actually a delta function. So something like this. So this is for people who have studied cutting rules. okay, would know that, this is what you mean by cutting propagators. It's basically what happens if you take one of these propagators and put it on shell, okay, where you impose the delta of p square plus m square. And of course, there's a propagator also with the left going to right, where the p is taken to be minus p. So you see there are, and this is basically the main subtlety. Apart from that, you can just use the usual Feynman rules and calculate. So these rules are actually the rules, by Weltman. Okay, so Weltman reinvented these rules when he was trying to prove unitarity. So if you look at the book by Weltman on quantum field theory, Diagrammatica, or Diagrammer, which has some notes, okay, and you look at the sections on unitarity, you'll notice that, Weltman basically writes these rules down, okay, and so basically because Weltman, when you're interested in cutting rules and Katkowski rules, one is interested in calculating imaginary parts of certain amplitudes, and the imaginary parts of certain amplitudes basically needs the amplitudes minus the complex conjugate of the amplitudes, obviously, okay, and so what Weltman means is a way to calculate, both the amplitudes and the complex conjugates, and if you think about it a bit, like Weltman did, you end up reinventing these rules. Okay, so these are exactly the rules of a unitary Schwinger-Keldysh quantum field theory. Now you can do this similar thing for any quantum field theory. But notice one very interesting fact, which is important, which is that, there are no cut vertices. In the sense that, so by cut, I mean something which links the left and the right, okay? For example, there's no vertex for, where, you have two right fields going to two left fields, okay? So this guy is not allowed, okay? And doesn't appear. So all the interactions are through propagators, okay? And this is a hallmark of unitary theory. And in fact, it plays a very important role when Weltman starts understanding the unitarity. Let's say if you want to prove unitarity of FIFO theory following whatever Weltman describes, okay, then it's important that there are no such vertices in the rules in the unitary quantum field theory, and that's what makes FIFO theory unitary. Okay, so one way of thinking about asymptotic states is a bit. It depends on what you mean by asymptotic states. So obviously, in some sense, you can cut this path integral at some time slice, and you have two copies of Hilbert spaces of a single quantum field theory. But yeah, but what allows you to calculate is this kind of correlators. Now, of course, this includes, let's say if you want to calculate the S matrix, you can calculate it by using a time-ordered correlator and taking an appropriate limit and so on and so forth. But yeah, so it depends on what you mean by asymptotic state. I guess that's the short answer. So anyway, so to continue, one way to understand an open quantum system or an influence functional is basically.
Yeah. So this is these kind of diagrams. If I just say I'm doing a bubble expansion, so then can I have two left particles going to two right, something say a bubble, and so in the propagators in between the solid line becomes this dashed lines.
Yes. So there is a sense in which, of course. See, this doesn't mean that the left, right correlators themselves are zero.
Okay, only at the tree level this is not allowed.
Okay, but there are no vertices. Okay, so of course they're not zero because of propagators like this. For example, you can of course have something like this, which are just made of things that I've drawn. Okay, and in fact that is the point. The point is that once you integrate out. The environment, actually, in the quantum field theory that you have, you do generate these vertices. So these vertices, which are cut vertices, are what I call as Feynman-Vernon vertices. And Feynman and Vernon realized that in some sense, when you integrate out an environment, okay, in the resultant effective theory, if you want to or resultant theory, if you want to calculate things, you have to include such vertices, which is basically the statement that once you integrate out the environment, and the environment is not, and there's some entanglements and so on, and it's affecting the quantum field theory, then the resultant evolution is non-unitary. Okay, so which means that like the Feynman perturbation theory, the diagrammatic perturbation theory should also be non-unitary, and one of the main ways that non-unitarity comes is that like you start including such vertices also. So that's one way where the non-unitarity comes. There's also another way the non-unitarity comes, which is that like these guys can become complex. For example, if lambda is complex in a real scalar field theory, then you know that it's a non-unitary theory. So there are basically like two kinds of non-unitarity. One is cut vertices, okay, and another is that like there is complexification of the usual vertices, okay, and these guys become complex, and then like this guy becomes lambda star, and this becomes lambda. So basically like you can add to this if this theory was not a theory on itself, but it was obtained by integrating out some other environmental field, say some chi field, okay, then you would have a term like Fe, so you can have a term like phi r phi L, where let's say this term is like some lambda delta phi r square phi L square, which is the kind of term that I have introduced here, okay. So that and what Feynman and Vernon did was to basically show how this kind of a theory comes about. Of course, he did it in the context of quantum mechanics, and I'm kind of interpreting it at the level of diagrammatics and so on and so forth. But this is essentially what Feynman and Vernon did. Okay, so basically, like they argued that the unitary structure of the Schwinger-Keldysh effective action gets modified by new vertices which couple left and the right fields once you integrate out some environmental fields. Okay. Right. So in the vacuum, actually, like of course we know that like if you integrate out a very heavy field, the theory that you get is not a non-unitary theory. In fact, like all of effective field theory is based on integrating out heavy fields around vacuum and getting unitary effective field theories. Okay. So the point is that you can calculate the Feynman-Vernon vertex in that case, and it will turn out to be 0. Okay. So often, like for the environmental influence, the environment itself should be a light field. It's a kind of a field that you would not usually integrate out, or that if you integrate that out, you will not get a unitary description. Or you can also integrate out heavy fields, and like in some other states where the heavy fields are populated, where there's an entanglement. See, the point is that like when will the system evolution become non-unitary? When there's an entanglement between the system and the environment. Yeah. Okay, then like and the entanglement is changing with time. Then you would see that like you cannot just get a unitary evolution for the system, and so you can start with such a state, okay, and trace out the environmental degrees of freedom, and that would produce a Feynman-Vernon kind of a coupling. Okay, so this comes to some other question. That is, let's say like if you're integrating out something light or something that you don't usually integrate out, okay, to generate this kind of non-unitary couplings, then like there are various questions that arise and which kind of are not very well understood. Okay, so you can now like open your favorite quantum field theory textbook and ask how much of what is there in that quantum field theory textbook starts applying to such an open quantum field theory where there's a non-unitarity. The one question which immediately occurs, let's say like if the fields that you're integrating out are light, is that like is there even a local effective action, right? So because we know that if you just take some random quantum field theory and integrate out some number of fields which are not very heavy, which are kind of this can be produced on shell, then like if at all you can write on effective action, the effective action is often not local. Okay, there's a non-locality. In fact, if you integrate anything, there's a non-locality. But if it is a heavy field, you can do an expansion in 1 over mass of the heavy field and get a local guy. And that's a question. Which I don't think we understand very well. Okay, that is that in which context do you even get a local like effective field theory? Okay, but you can say that okay, let me not worry about it, and let's say some environment gave me this additional vertices, some local effective action, So then you can ask another question, okay, which is the next question that you usually do in quantum field theory. Say there is a local effective action, you write down, okay. So how do usual notions of basically renormalization apply to this theory? Okay, so basically the question is that so do these couplings run? For example, does this lambda delta run that I have introduced here? Does it run in any sense? Is there a beta function? Is there a beta function for lambda and lambda star? Okay. Now you know, like, so you can ask such a question, and what does it mean? Okay. There are more general questions you can ask, you know, which is that, you know, what is the structure of the effective action? Okay. So the structure of the effective action, in the sense that, you know, like, is there a relation between lambdas and lambda delta? Okay, that is, which generically has to be true. Okay, are there some relations which come from microscopic theory? You know, how does it depend on the environment state? Let's say if the environment was a thermal environment with temperature T, how does it depend on the temperature T? Right? You know, like, that's a kind of question those are the kind of questions that arises. And one of the things that I'm interested in is basically trying to understand these questions. Okay, so there's also you know, like you know, like a slightly more recent question, which you can ask, you know, like which is that, you know, like, this standard Schwinger-Keldysh formalism and integrating out fields, like the way the Feynman and Vernon have described, okay, in their paper, in their work, you know, like in 1960s. How does it generalize if the thing that I want to calculate is not just, say, time-ordered correlators, or maybe time-ordered correlators and anti-time ordered correlators of this kind, but if I want to also keep track of out-of-time ordered correlators, okay. So, you know, like, if I want to keep track of out-of-time ordered correlators, how does this change? So, you know, like, there's one thing that you can do. You can easily generalize this Schwinger-Keldysh formalism for the unitary theory, you know, like, to out-of-time ordered correlators, which, in fact, you know, like, some of the out-of-time ordered correlators which have been computed are computed this way. And the way you do it is by just including more and more legs here. Okay, so basically what you do is that instead of the time contour, the Schwinger-Keldysh time contour, okay, that is here. Okay, so what you do is that, you know, like, you have, let's say, you know, like, many time contours. Let's say you have some k time contours, so with some 2k number of fields. So you have like some phi 1, phi 2 until phi 2k. Okay, and then, you know, like, you can put something like s of phi 1 minus s of phi 2 plus s of phi 3 minus s of phi 4 and so on and so forth. Okay, in the exponent. Instead of what I've written, s of phi r minus s of phi l, and then, you know, you can put the appropriate boundary conditions. Yes.
So there you said that maybe suppose in some case we do have a local effective action after integrating out, then what is the notions of renormalization? So you said that in general we don't get an effective action when we do integrate out. So when you are saying that we will get it, so doesn't that restrict some aspects of how those couplings can be renormalized? Because not all of them can be renormalized, otherwise it will again become non-local, right?
Yes, I think there are some restrictions. Unfortunately, I don't think, you know, like, you know, like, I'm not going to answer any of these questions very detailed. Okay, so at this point, you know, like, we do not understand these structures very well to actually answer any of these questions to the kind of satisfaction we have about quantum field theory. Of course, quantum field theory we understand because we have been studying it for you know, like, about a century. Well, slightly less than a century. And the point is that, you know, like, so there are many questions of this kind, okay, which you can ask. In fact, you know, you can open your favorite quantum field theory textbook and you can ask, you know, this page, how does it generalize? And often it's not very well understood. So I will tell you about what I do understand, okay, but there are many things which are not understood, okay. So one thing I do understand is that, you know, like, in a unitary quantum field theory, if you want to compute out-of-time ordered correlators, what you can do is that, you know, like, you can generalize the Schwinger-Keldysh formalism. So this is the generalization of Schwinger-Keldysh formalism, and you can write down a path integral if you want to compute it by a path integral. There are also various other ways of computing it. You can try to compute it in the Euclidean theory, analytically continue, if you have enough control to do that. Okay, but if you generally want to do perturbation theory, often it's useful to just start with this formalism and do it. Okay, anyway, so the point is that you can start with such a thing, and then you can insert various operators, and then what this guy generalizes to is that you have some arbitrary number of time orderings, anti-time orderings, k number of times. Okay, if you take 2k folds, and if you want a correlated like that, then you can compute it by such a thing. So basically, the generalized Schwinger-Keldysh formalism is basically there's a generalized Schwinger-Keldysh formalism, let's say, okay, with k time orderings and anti-time orderings. If you want to calculate the correlator, you can calculate it. So what you can do is that you can repeat what Feynman-Vernon did, okay, in case of in this kind of path integral, and then integrate out fields, and what you will generate is a generalized influence functional. Okay, so what you will do is that generate Feynman-Vernon functional, so which basically ends up coupling all these guys. Okay, so that's just a generalization of what we already know. And you can ask similar questions about these correlators also. Okay, so this is as far as the basic formalism goes. Okay, so let me just pause for a minute. Okay, and ask why one would be interested in computing this kind of thing for out of time ordered correlators, or even for Schwinger-Keldysh correlators. That is, what is the kind of physics that one aims to understand, okay, by trying to answer these questions. Okay, so one point is, of course, why do we want to trace out an environment? Because usually the environments are very complicated. Like why do we want to do effective theory at all? Because usually the full theory is too complicated and you don't see various structures. Sometimes things don't depend on what environment is doing. Okay, there's a universality. Okay, sometimes things are not things depend on the environment in some very specific way, and you might want to understand this system as a kind of a probe towards the environment. For example, let us say I have some big system, okay, which is the environment here, and there are some correlations in the system. Okay, it could be time ordered correlations, out of time ordered correlations, and so on and so forth. Okay, and one is interested in, let us say, what a small system which is coupled to this will do. Okay, so a simple example of this, which often statistical mechanics people like, okay, is that you have, let's say, a bath of water or any other liquid, any other fluid. Okay, and you have a simple particle, some Brownian particle, which is left in the water. Okay, so the water, let's say, or any fluid, is in a thermal state, and because it is in a thermal state, the correlations in this fluid are thermal. Okay, so usually if you have a thermal environment, okay, there are thermal correlations. Okay, and what these thermal correlations mean is that and these thermal correlations, of course, affect what the Brownian particle sees and how its evolution is affected. Now, if you know your Brownian particle, so what happens with the Brownian particle is that you can write down some kind of an effective description where you have some damping, right? Okay, and you have some noise. So you have some a force, which is a noise, and then you have some damping, okay, that the Brownian particle sees, and this noise is often is taken to be Gaussian. So basically this expectation value. So this is some ensemble. This is drawn from an ensemble where the ensemble averages are such that there's a Gaussian correlation. So this is a Gaussian correlated, okay, noise. So it's a random noise, a Gaussian noise. And the point is that if the Brownian particle is moving around in a thermal bath, a thermal this thing, okay, there's a standard statement that actually these two things are related. So this is what is called the fluctuation dissipation relation, which relates the dissipation that the Brownian particle sees and the fluctuation that the Brownian particle sees. Okay. For the fluctuation, the forces, the fluctuating forces, the noisy forces that the Brownian particle sees, which renders its path a stochastic path, in the sense that, like if you put one Brownian particle, if you see what it does, if you put another Brownian particle, it will do something else. Okay. But but you can still calculate an ensemble average by putting various Brownian particles and see what they do. Okay. And this fluctuation dissipation theorem is really a statement of actually thermal correlations. So this is something that Feynman and Vernon pointed out, and in fact, it was one of the motivations of why Feynman and Vernon studied this kind of a system. And the statement is basically that, so let's say, you think of this particle as being coupled to the environment by an operator. So there's some environment operator, okay, and then, let's say X. So the X is the X of the particle. Then basically, what you get is that, the Feynman-Vernon functional basically takes the form where you look at some contour ordered correlator of this environment operator in the thermal state of the environment, okay, and then you have basically something like so X, and so this is X and X, okay, so this is in some frequency space and so on and so forth. So you can say omega 1, omega 2. This is a function of omega 1 and omega 2. Okay, so integral d omega 1. So this is, you can imagine why this happens. Basically because X couples to A, and then you have a 2-point function which gives you a term in the effective action of the system of this kind, and hence and this 2-point function is what causes both this damping and this noise term. Okay, and the way that so this should also come with some indices. So these are all various. So there's x1, x2. There is a phi 1. There's environment 1, environment 2, depending on which Wiener-Keldysh contour you're looking at. But the point is that so the relations, okay, obeyed by these thermal correlators. So relations of these thermal correlators, okay, is what obeyed by the environmental correlators is what actually leads to the FDT of this system. Okay, that the damping that is seen by the system, and there is a dissipation seen by the system, and the fluctuation seen by the system are actually related. Okay, and hence you can, for example, try to study this kind of a thing. Okay, so if you want to study Brownian particle, so this really does not depend on the system, what the thermal bath is. Because the only thing that you're interested in is that whatever the system is, it might be water or some other fluid, but independent of what it is, there are some universal relations that correlators calculated in the thermal state, correlators of this kind, should satisfy. Okay, and from that you can actually say something general about the system, which is how does the fluctuation and the dissipation of the system work. Okay, so this of course somewhat standard stuff. But this is one reason why Feynman were not very interested in it. So one reason you might be interested in this thing for a general out of time ordered correlator is to actually understand whether what is the out of time ordered version of this fluctuation dissipation theorem. Okay, so you can ask so what are the OTO version of the fluctuation dissipation theorem? Okay. So of course, they should come by looking at the relations of the thermal correlations in a thermal bath of out of time ordered correlators, and in fact there are such relations. Okay, so generally, so how do these relations look like? So let me just give you an example. One example I've given is that among the 2-point function there's a relation. So generally the fluctuation dissipation theorems take this form. That is, let's say you're looking at some correlator, some n-point function, okay, of this environment, okay. So let's say, at some time t1, t2, some Weitmann function. So you're looking at something like this, okay, where this t1 to tn can be of any order. And depending on how away they are from time ordered, there are more and more out of time ordered correlators. In fact, you can ask, and more and more out of time ordered they are, you need more and more contours to calculate them. So in fact, you can ask what is the minimum number of contours required to calculate a particular correlator. So if it is k, you say that it's a k out of time ordered correlator. So for example, Schwinger-Keldysh correlators will be 1 out of time ordered correlator this way, and the chaos correlator would be, or the double commutator, the commutator square would be a 2 out of time ordered correlator. And you can calculate, like what is the general out of time ordered correlator, which is a k out of time ordered correlator. But anyway, never mind. So let's say, like if you're calculating such a correlator in a quantum field theory at some, like in some temperature, finite temperature state, where this beta is basically the t equal to 0 state is actually given by the thermal state. Okay. So the fluctuation dissipation theorem basically says that, like these kind of correlators are basically given by, can be written in terms of expectation value of commutators, so nested commutators. This is one thing. So let's say, like you can have so this is a kind of a nested commutator A, B, C, D. Okay, and now since I don't want to put all these brackets, let me just denote it by A, B, C, D. So then I can just say that this is just A of T1, and A of T2. Let's say some permutation of 2 to n. Okay. So this is a permutation of n-1 operators where the sigma is it belongs to some Sn-1. Okay, and times some coefficients which don't depend on, which are independent of the quantum field theory, which only depend on the temperature. Okay, so what this tells you is that on left hand side you have n factorial possibilities where you can just rearrange these orderings in n factorial base. Okay, so this is some n factorial quantities. Whereas like on the right hand side you have basically permutations of n-1 objects. So these are n-1 factorial quantities. Okay, and one way to understand fluctuation dissipation theorem is the statement that if you are calculating thermal correlators, okay, you can actually reduce these n factorial quantities to n-1 factorial quantities, and basically so that's those are the relations. Okay, so which means that there should be relations between n factorial quantities. If you write n factorial quantities in terms of n-1 factorial quantities, for example, this means that the anti-commutator, in particular, in 2-point function can be written in terms of commutator, and that's what leads to this kind of a fluctuation dissipation theorem. Okay, so what you need is to ask, like what this kind of relation. So this is the kind of fluctuation dissipation. This is the kind of relations that. So if you want the coefficients and so on, in fact, one can write these coefficients very explicitly. I would ask you to look at this third paper, where we worked out an explicit relation for any n-point function once for all, which basically tells you that this thing. Basically, what it involves is some very Bose-Einstein factors and so on and so forth. Okay, which I don't see much point in writing down. But the point is that you have such a relation. And what this relation means is that there is a structure to the thermal Feynman influence functional. Okay, and the point is that and this structure leads to some kind of generalization of fluctuation dissipation relations. Okay, now so in fact you can actually ask what these are. So basically what you would see is that there are some. So for this is just the linear term. You can add the nonlinear terms, nonlinear damping terms, things which go like x square x dot, let's say, things which go like x cube. You can also add noise that depends on x and so on and so forth. And what you can do is that and what you would like to do is that to actually derive the analog of this kind of a fluctuation dissipation theorem for a general for a general Langevin kind of a theory where you keep track of all these nonlinear correlations. Okay, so one another motivation for doing this is that let's say the system was not thermal. Okay, or even if the system was thermal. So what this does is that it just reduces a certain set of correlators to a certain set of correlators. So it gives relations between the two. But you can also ask explicitly what is the damping. Okay, and what this damping tells you roughly is that it tells you a response function. It just measures the expectation value of the correlators, of the commutators of this thing in the environment. Okay, so like another way to do it is to actually measure this commutator itself. Okay, so in like which is also useful. So for example, like this is how you try to. I mean, the original Einstein's paper on Brownian motion was about like using the fact that both gamma and F noise characterize different properties of the water or whatever it is, and then and use that to say that say to calculate the Avogadro number. Okay, so that's one of the things that originally you did. But the point is that like one might hope that that by measuring such responses in the out of time ordered version of the Brownian particle, like what you can do is that you can hope to measure the out of time ordered correlations in the bath itself. Okay, of course there's no reason you can generalize this statement also to the case of the environment not being thermal. Okay, which is much more of a pain, and it's taking us much more longer time to work out various things. But the point is that like in principle, I think we will be done at some amount of time. And the point is that like and what we would like to know is that like whether you can use such a kind of a probe to measure these out of time ordered correlators. This is kind of an important question, I think, because while we talk about out of time ordered correlators in various different ways, we do not really have very efficient ways of measuring out of time ordered correlators. Okay, so most of the things that people have talked about in measuring often involve basically like going through this kind of a contour, like literally in the experiment, in the sense that you evolve a system forward and you evolve it backward, which you can in principle do. For example, if you have like if you have a spin system with a Hamiltonian like this, you can just invert the magnetic field, and that will take h to minus h, and you can just apply magnetic fields. You can measure some things, and you can you can reverse the magnetic fields. So that's the kind of thing that people have been doing. But obviously, this is a very kind of a special kind of Hamiltonian. So even in free particle, we do not know how to reverse the evolution in an experimental sense. Okay. So what you might hope is that like you can take such a system where you can indeed reverse the thing and measure out of time ordered correlators and use it as a probe, couple it to the favorite system that you want, where you can't actually reverse the evolution. Okay, and basically like derive some effective action for the probe, which is moving in this big environment. Okay, and by looking at this out of time ordered influence functional, you hope to learn about the correlations in the system. Okay, so of course if that happens, that would be very nice, in the sense that like if somehow we can convert the out of time ordered correlations that are in a big system, which we can never practically hope to reverse the evolution of, and convert it into, I mean, that's the kind of thing that makes something measurable. Okay, and that's one of the things that one would like to do. Okay, so like I have a few more minutes. So this has all been somewhat very vague, but like like some of the things you can actually check that like there are various these relations and so on and so forth. You can derive explicitly, but let me just so conclude. Okay, so basically like what I was telling you about is a particular class of functionals, and how do you think about basically this basic problem where you have a system and which is coupled to the environment, and how do you think about that in a quantum field theory or in a general quantum mechanical system, and the way to do it is to actually like was at least in a particular for time ordered correlators, it was described by Feynman and Vernon. Okay, and it also has the way of thinking about Feynman and Vernon. It also has natural understanding in the terms of cutting rules and so on and so forth. Okay, Schunke-Keldysh and Feynman and Vernon. And the main thing that I wanted to say is that like many of that can be generalized. Okay, so though like there's a whole bunch of questions which we do not know what the answers to, which is that, you know, like how do you do renormalizations in this theory, and how do you do how do you derive local effective actions, and when do you get local effective actions? So let me just make a few comments about this renormalization. Okay, so let's say, you know, like you have some effective action which has some frame member non-vertices. Okay, so one of the things that we did, which you will find in one of these papers, is to look at renormalization of open 5-4 theory. Okay, so let's say, you know, you have a, let's say, you know, you look at what I call as an open 5-4 theory. Okay, which is basically a theory where you have basically 5-4, but you know, like you also add the frame member non-vertices. Okay, so the frame member non-vertices, the most general theory, are of this kind. So you can have something like this. These are the vertices. These are all left, right, and then of course you can have the vertex like what I've been telling you about. Okay, and the point is that, you know, like apart from plus the usual vertices for the left and the right. Okay. And you can do a perturbation theory, okay, and when you do a perturbation theory, you start getting various loops, okay. In particular, let's say, you know, like, so many of the loops, some of the loops are finite, okay, actually, because, you know, like they are just cut propagators, and people who know that, you know, like, for example, this loop is just a cut loop, and which is just the imaginary part of the usual loop, okay, and that is just finite, which Weltman knew, which you can find in the Weltman's paper, but Weltman's book, okay. But some correlators, and now of course this kind of a loop is of course not finite. There's a usual 5-4 kind of a loop, so it's not finite. It has some divergence, okay. But then, you know, you also get loops which are of this kind, you know, like, so let's say you have a loop there. One of the propagators is cut, and another is not cut, okay. So this is not the kind of loops that you usually worry about in a standard quantum field theory. So this kind of loops occur if you take the imaginary part of this guy, okay. But this guy does not occur in any sense. In fact, this loop is, you know, like if you try to write this loop, so this is just an integral, which is like d to the power dp, d to the power, you know, like one of the integral is p square plus m square, okay. Another integral is a delta function, something like theta of q0 delta of q square plus m square. I'm not writing the factors. And then, you know, so this is a k, then you have a delta function of p plus q minus k. Okay, so something like that, okay. Now you can analyze this loop, let's say in d equal to 4. You can do a dim reg and analyze this loop, and you will find that, you know, this loop has a very funny behavior, okay. In fact, you know, like if you analyze this loop, let's say in dim reg, so you will get the usual 1 by d minus 4, some factors. Okay, and you will get something like, okay, just to make a point, let's say, you know, like these two masses are different. Let's say m1 and m2, so that this is m1 and this is m2. Okay, so you'll get something like k square plus m1 square minus m2 square divided by k square plus finite. Okay, so this is a calculation. So this already tells you that this loop is kind of quite a sick loop in some sense. Because what you see here is like a usual 1 by epsilon of dim reg, okay. And when you have 1 by d minus 4, usually in dim reg, whatever multiplies it is usually a polynomial in the momenta, okay. This is the basic statement that, you know, like this kind of divergences, you can put a counter term, a local counter term, okay, and cancel them, okay. And in fact, you know, like you can argue that this should be always true in the usual quantum field theory, basically because, you know, you're usually having some number of you know, propagators in the denominator, okay. And if you sufficiently differentiate with respect to the external momenta, then you should get rid of the divergence, which basically means that the divergence should be a polynomial in the external momenta. Okay, so this is a standard statement in quantum field theory. But once you start doing open quantum field theory, okay, you run into this kind of a loops, and this is a loop where you see that, you know, like this divergence is not really local. And let me emphasize that this is worse than say having a non-renormalizable theory, because non-renormalizable theories are not theories where the divergences are non-local, but it's just that theories where, you know, you need to add more and more counter terms as you do more and more calculations. Okay, so this is worse than a non-renormalizable theory. It's you know, it's more like I think the only example I know of where such things occur is in non-commutative theories. Okay, so in a certain sense, these are probably like non-commutative theories, though I do not know how to make this statement precise. Okay, but the point is that there is but it is local if M1 equal to M2, so which means that M1 equal to M2. Okay, theory you can actually renormalize, you can calculate the beta functions and so on. Okay, but if you have M1 not equal to M2, okay, then you have non-local divergences like this. Okay. I have integrated out the environment. So this is just the system.
And that vertex that you have there on the left is what kind? I mean, why do you have a vertex between solid lines and dotted lines?
Because this is an open, this is a non-unitary theory. Okay, so the phi itself. So let's say the way I'm thinking about is that there's a phi plus some chi, some environment. Okay, and which I have integrated out. Okay. And I have written down some effective theory, like the theory that I written down, just with some Feynman non-vertices. So this is a Feynman non-vertex. Indeed, this theory, this kind of a loop, never occurs in a unitary theory. Okay, let's say let's say you're just looking at this guy. Okay, so this guy is a Feynman non-vertex. Okay, because it's a cut vertex which never occurs in a thing. But if you start trying to understand renormalization in this non-unitary theory, okay, which you might think of the effective theory of after you integrate out like certain set of fields, basically like a la Feynman-Vernon, then and if you start doing perturbation theory with that non-unitary effective action, then you run into integrals like this, okay, which don't have the nice analytic properties of the usual quantum field theory, and hence which do not quite have this thing. So like there are various confusing things about trying to understand renormalization in here. So sometimes you can get renormalization. In fact, like you can also do this for fermionic theory, and you can show that like you run into similar problem. Basically, fermion, say some open Yukawa theory where you have fermions and scalars coupled. Then you run into the same problem because basically of this loop. And the question is to understand what does this loop mean, and maybe there's some maybe there should be some way of dealing with this loop, like this kind of things can be dealt with in a non-commutative theory, or I'm not even sure like I understand the physics of why this happens, except that this is kind of very simple. It has nothing to do with you just have to evaluate this integral. You cannot quite analytically continue this integral to the Euclidean theory because it's not quite analytic and so on and so forth. But you can integrate, you can evaluate it in the Lorentzian theory. And argue that this is the kind of divergence that you have. Anyway, so let me I see that I have run out of time. So let me just stop here and take questions.
So it's just a comment. I'm not sure how useful it will be, but when you had this kind of mixed propagator. Mm-hmm. You said there's no propagator, but you have delta function, which is basically putting those things to on cell. When you have the problematic kind of loop, they look like very much. I mean, this generalized unitarity cut method, when you rather than cutting everything, you just cut one of the lines, or you cut as many lines as you want, and these are the lines you cut to compute, say, coefficient of the tadpole diagrams or something like bubble diagrams, etc. separately. So this kind of integral do appear. I mean, people like.
Well, usually I thought, maybe you can correct me if I'm wrong. Usually I thought you just even in general unitarity you just cut it cleanly into two parts. You never have this is like a dangling loop. You cut one propagator and it doesn't cleanly divide. I don't think okay. At least I don't know of a place in unitary quantum field theories where you see these loops. Though yeah, there should be some other way of thinking about this thing. But yeah, but this is kind of relevant. Like whenever somebody writes down an effective action for any non-unitary theory. Okay, this is of course a very simple example. Is where the non-unitary theory is a FIFO theory. Okay, but this also shows that like if you just look at effective actions for, let's say, like and Mukund and various other people have been talking about for fluid dynamics, which is really, in one sense, a very complicated version of a non-unitary theory. And if you start doing loops there, I think you will find this. So So this of course a very, like a baby version of it, okay. So like this thing should be understood to even make sense out of, I mean, of course those you can use those effective actions to do tree level calculations and so on, but usually you write down effective actions to start doing loops. And somehow people do such things, and it has never been, I think, or maybe there's some way of understanding it which we are not doing it correctly. Yeah.
You have the diagram where M1 and M2 are exchanged, right? Don't you get the opposite sign?
Yeah, but you also get, let's see, you also get different vertices, I thought. Let's see. This is easiest to do if you have so somehow you maybe it does cancel in this diagram, but there are diagrams where it doesn't cancel. Okay, I'm just trying to remember. But okay, one way to one another diagram is that let's say this diagram is actually a fermion. Okay, then what you get is that you get some prefect which is made of Dirac matrices, which doesn't quite cancel. Yeah, but. So and also the vertex factors are different actually. So let's see. So if this M1 M2 are, in general there's no reason that this vertex should be the same as this vertex. So here M2 M1. So this vertex need not be equal to M1 M2. Right? In general they are not equal. So these two diagrams with M1 M2 exchange actually comes with a different vertex factors. And hence it doesn't cancel. I think that's what happens.
So you also generate cubic vertices in doing the integrating out to the environment, right? I mean, because
yeah. So this is in a 5-4 plus 5 cube theory. Like you can, I mean, it's actually
there are,
in open 5-4 theory. You can, I mean, the generalization between cubic, quartic, and so on and so forth. They don't make much difference. It depends on whether you impose phi going to minus phi symmetry. It's like the usual 5-cube, 5-4 kind of theories. Yeah.
And also I had a question that the action that you had written down, this S phi L and S phi R, were they of equal masses to begin with in the path integral?
So the unitary theory, of course, has equal masses. So basically you have something like m square phi r square minus m square phi l square.
Yeah.
So in the non-unitary theory, what will happen is that, this m squares will become complex, and you'll get m square phi r square minus m star square phi l square. And then you'll also get some Feynman non-coupling, which is like m delta square phi r phi l. Okay.
Okay. Okay. I see. So the splitting of the mass gives two different mass eigenvalues, which is why you have two different masses.
No. So in a single mass theory, everything is fine.
Yeah.
Okay. You can just take this m square is just complex m square, so everything is fine.
Yeah.
Okay. Or you can take it to be real m square and take the imaginary m square to be small. But so in fact, the open phi 4 of a single phi is fine. Like some of these divergences cancel out, and you can actually calculate the beta functions and so on and so forth, which we did in this work last summer. Okay, but what happens is that like once you start having two different kinds of fields, let's say fermion and scalar even of the same mass, okay, or you start having like two scalars of two different masses. You run into trouble, run into this kind of loops, which have these funny divergences. Okay.
Thank you.
Read out some degrees of freedom, namely that of the environment. So you wouldn't expect all the counter terms to be local anyway, right? Means you have integrated out some degrees of freedom. Write down an effective theory. So.
Yeah, but it's an effective theory.
Yeah.
The question is, I mean, so one might be you can just say that this effective theory is not local once you take quantum corrections into account. I don't know whether that is the correct way to say it, but it's also that like there's some effective field theories which work fine, like a single scalar theory with this masses, where yeah. I'm not sure whether that is the resolution, but.
Okay, if there are no further questions, then let's thank Loga once again.